today we're going to talk about recursion. This is intended for the grade 12 university level course, but if you're here a little early, that's great too. So the goal today is to go through a new programming strategy to solve various problems. Now let's take a quick look to see how we go through this. First of all, let's take a look at this code here. Imagine you have this subprogram. Very simple. It's called stuff. It takes a simple parameter of size n, integer n. Doesn't do much, it's not meant to do much, but let's take a look and see how it works. It says as long as n is a negative number, return the value 1. Otherwise, return stuff n. So let's think about this for a second. If we have over here on the left side here, let me see, let's say we have a value of 4. Now if we go into that subprogram on the right hand side here, it says, hey, is 4 less than or equal to 0? No, it's not. So it's going to skip this and it's going to return stuff again with a value 4. So it's going to call stuff and have a value 4. Say, well, is 4 less than or equal to 0? No, it's still not. So return stuff again with a value 4. Come back up. Is this less than 4? Is it less than 0 yet? Nope. What you can see here is this is never going to end. What we've done is we've essentially created an infinite loop here. Well, that's no good. So what do I mean by potentially create an infinite loop? Well, if we entered a negative number, that would be fine. We would just get a value of 1 and everything would end, no problem. But as soon as we entered a positive number, nope, no dice. That's no good. So what we've created here is basically this cycle, this circle that goes on and on and on itself. That's no good. This will actually crash your program, and it's called a stack overflow. It basically means that we're out of memory. Every time you call a subprogram, it puts a little bit more memory onto our stack of data that's currently being accessed or being used. And eventually that stack overflows. Think of it like a cup. As you put more and more water in, you eventually get to the top and over the edge it goes. So that's no good. Now let's modify this a little bit. We still have this same endless loop of subprograms here called stuff. I'm going to make one small change to this. Let's see how that changes things. So the one thing I've changed is this little piece right here. All I've done is say, well, instead of passing exactly n, pass one smaller this time. So let's go through this. Imagine we started with that value 4 again. And we said, all right, is 4 less than or equal to 0? No, of course it's not. So we come down here and say, well, return stuff of 3. Okay, well now we're doing 3. Now it comes back in here, comes back up. Now n is a value of 3. Is 3 less than or equal to 0? No. Comes down into here. Well, okay, well let's try a little bit lower then. Let's do stuff of 2. Still no dice. So we come back up, come in here. Well, is 2 less than or equal to 0? Nope. Let's try it again, but this time with a value of 1. Now over here, we come back up. Is 1 less than or equal to 0? Still not. Still not. So we come down in here, and we say, okay, well, this time, let's try it with a value of 0. Okay, so we started with 4, we went down to 3, down to 2, down to 1, and down to 0. And this is all our value of n. Great. So now we have a value of 0. So 0 comes in. Well, is 0 less than or equal to 0? Well, it most certainly is. So let's return a 1. So right here, this step is going to return a 1 up to the previous step. Well, that just says return the result of this. Oh, well, that's a 1. So that 1 then gets pushed up to that previous step. And this cycle continues, and it's going to get passed all the way back up the chain. That same 1. And eventually, our result of our whole thing is a value of 1. What that tells me is that no matter what, when we run this code, we are going to get a value of 1. But that's not the point here. The point here is how it executed. We started with this value 4. And this value 4 said, okay, well, let's go all the way around, but this time, let's not do a 4. Let's do slightly smaller. Let's do 3. Go all the way around. Let's try 2. Go all the way around. Let's try 1. Go all the way around. Let's try 0. Ooh, that's a good one. So now we're going to say, oh, we got a good one. Let's work our way back out. So that value is going to come back out the spiral. Eventually, oh, my drawing is amazing here. That's going to spit out that final result of a 1. So what in essence we've created here is, instead of an endless loop, we've created a spiral, something that works towards a goal. In this case, that goal was this n is less than or equal to 0. So what is recursion? That's kind of what the whole point of this is, right? Getting a little closer here. So that spiral is what recursion really is. The act of a method calling itself on a smaller version of the same problem until it gets to a stopping point. We saw this in the previous example. We started at a value of 4, then went down to 3, 2, 1, 0, which was our stopping point. That was our base case. A value of 0 said, we're done. Give a value of 1 back. We don't need to go any further. That method calling itself is called the recursive case. The stopping point is called the base case. These are key terms you need to know. Recursive case, base case, and recursion itself. Those are very important. So let's look at a real-world example, for example. Real-world example for a short second. Now let's think about this. Trying to eat your dinner. Now when you sit down at the table, you got a plate full of food in front of you. The first thing you say is, well, is my plate empty? If it is, stop eating. You're done. There's no point in going any further. Stop. However, if it's not empty, eat one more bite. Just one more bite. This is our step towards that base case, and that's important. That's what brings the spiral down. And then finally, repeat the process. Eat your dinner, but this time we're working with a smaller plate of food now. There's less food on our plate. So the whole process begins again, but now with less food. So it comes back and says, is the plate empty? If so, stop eating. Otherwise, take another bite. Rinse, repeat, repeat, repeat. And every time that plate is having a little bit less until we get to the point where the plate is empty. And then we're done. That's recursion in a nutshell. Our job is to be able to code that, of course, though. Now there's a couple quick points. What if you never actually hit that base case? What if you have an error in your program? What if some joker keeps putting food on your plate when you're not watching, right? This can happen in real life, of course, but also it can happen in our program. We make some kind of mistake, some kind of error in our situation where it causes an issue. Well, in this case, we get what's called infinite recursion. Same thing as infinite loop, but it's what we saw when you have a function calling itself, calling itself, calling itself, and never reaching that base case. We've run out of memory. We keep stacking on top, and we just run out. We get that Stack Overflow error again. So let's talk about recursion. What's the truth about it? Well, the truth is a little bit more glib. Recursion is not useful very often. However, when it is, it can produce an extremely elegant solution, something that's easy on the eyes, easy to understand. Now that doesn't necessarily mean that it's more efficient, though. It just means it's more elegant to look at, more elegant to write. So something can be written in very concise manner using recursion at times, whereas the iterative or looping solution may be much more complex to read. We only use recursion when it makes sense to break up the problem into smaller solvable pieces. It doesn't make sense to do so otherwise, because that's the point of recursion. Recursion isn't just a function calling itself. It's a function calling itself on a smaller version of the problem. That is very important. So the strategy of breaking up a problem is called divide and conquer, where you break it up into smaller pieces and then you bring back the solutions together to find the solution. So remember, anything you can do with recursion, you can also do with iteration or a loop. So you got to kind of make your decision of what to use based on the scenario sitting in front of you. And sometimes that's obvious, other times not so much. But just remember, both solutions technically will work. So some of the best uses of recursion that we see, we're going to definitely see later on this course, is sorting and searching algorithms. Those are going to be key. So let's take a quick example here. Now this is going to be the focus point for the rest of the lesson here, the idea of a factorial. So in math class, I'm sure you've learned what a factorial is, but basically here's a couple quick examples to demonstrate this. So, oops, one up on myself here. So if we have the normal case of 4 factorial, what 4 factorial is equal to is the number itself multiplied by all the numbers below it down to 1. So this is 4 factorial, which equals 4 times 3 times 2 times 1. Well, if we had something like 5 factorial would be equal to 5 times 4 times 3 times 2 times 1. 6 factorial would be the same thing, multiplied by 6. So 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. Hopefully you're seeing a pattern emerge here. Now there is a couple special cases that we need to look at. First of all, 1 factorial. Well, 1 factorial, that just means 1 times all the numbers smaller than it that are down to a value of 1. Well, there is no numbers smaller than it that are not already 1, so it's just 1. It's done. And then this special one over here, 0 factorial, is equal to 1. I'm not going to go into the math behind this right now because that's a little outside of the scope of the lesson, but take this as a truth for now. 0 factorial is equal to 1. So these are 2 special cases that we can think of. Now, so we have our normal case and we have our 2 special cases. Great. So we need to program a solution for this. Now, if you were just to do this as a loop, you would just say, oh, well, that's easy. I'm going to create a loop that counts down from whatever value I'm looking for down to 1 and just multiplies them. And that makes sense. So you do this and you get a solution that looks like this. So we're going to start with a result of 1. We're going to say, all right, let's loop from n, which is in this case, in this example, 4, and keep looping as long as I is greater than 1. Now, why do I say greater than 1? Why don't I go all the way down to 1? Because this would just give us 4, 3, 2. Why would I do that? Let me just make a little space over here so we can kind of write this out a little bit. So let's think about this for a second. We have a loop and we're going to say start at 4 and we're going to go down to 2. So that means we have 4, 3, and 2. Well, let's look at the logic here. So if we come in here, n is a value of 4. We say, all right, our result is currently equal to 1. Okay, now let's do our loop. Loop starts at 4. 4 is greater than 1, no problem. So we go inside of here and we say, okay, well, our result is equal to the current value of result. So result is going to be equal to the current value of result. Well, that's 1 multiplied by our value of I. Well, that started at 4. Okay. And then the loop goes back up and we say, okay, well, now I is another number bigger. So now our number is smaller because we're decreasing. So I is a value of 3. So is 3 greater than 1? Sure is. So we go in here and we say, okay, well, now result, which is equal to the previous value of result, which is just 4, multiplied by our current value of I, which is now 3. Well, that gives us 12. Great. Okay. So now we go through the loop again. I gets decreased again. Now I is a value of 2. So we come in here. We say, okay, well, now result is equal to the current value of result, which is 12, multiplied by our value of I, which is 2. Well, that gives us 24. So now we come back to the top of the loop, reduce I by 1. I is now equal to 1. 1 is not greater than 1. So we just return the value of result. So 24 gets returned. And that's accurate. 4 times 3 times 2 times 1 is 24, of course. Now, if you look at the way this actually worked, what we did was we ended up going 1 times 4, and then we multiplied that by 3, then we multiplied that by 2. Well, that's really the same thing as this. We just kind of did it in a out of order sort of fashion. Why did we do this? Why did we set result equal to 1? Well, we started 1 with this value so we could handle these 2 special cases. So imagine we came through this whole code and we set n is equal to 1. So it would come in the code and say, well, set result to 1. Okay. Set result to 1. We say, okay, let's set I equal to n. Well, n is 1, so I is equal to 1. Is 1 greater than 1? Nope. Immediately jumps out and just returns result. Done. So that takes care of that case. The exact same thing happens when n is equal to 0. So it comes in, sets I equal to 0. Okay. Is 0 greater than 1? Nope. So it returns result. Again, the value of 1 is going to get returned. Pardon me. So we can see that the looping solution is pretty easy. Just loop from the number that we started at, our n value, down to, but not including 1. And we just multiply each step through. Okay. Let's leave that there. What does the recursive case look like? Well, the recursive case is actually a little bit easier to understand. So we still have the exact same program signature, or function signature. Now here, I'm taking care of these 2 special cases first. If n is 0, return a 1. Or if n is 1, return a 1. No hard work there. We're just going to say, well, we're done. Just return a 1. No reason to worry here. However, if we're not either one of those special cases, we've got to handle this one. Now, if we see here, we're saying return n times factorial of n minus 1. What? Well, let's think about what this actually means here. Look at this 4 factorial for a second. So we have 4 factorial is equal to 4 multiplied by 3 times 2 times 1. Well, what's that? Well, that's 3 factorial. So if you look at this, we just did 4 times 3 factorial. Now that's going to go another level deep. It's going to do 3 factorial, which is going to be equal to 3 times 2 factorial, and so on and so forth. Now we'll go into more detail and dissect this in a second. But right now, we see that we have these two functional operations. So let's try and break this down, because the whole point of recursion is that we can create more of an elegant looking solution, something that's easier to read and easier to understand. Yeah, I would agree that this is probably a little bit easier to understand. This is shorter, maybe a little bit more complex though. I'm sure I lost a few of you during that explanation of the iterative solution. Over here, it's pretty straightforward. Is it one of these two cases? Then return 1. Otherwise, return the simple math here. The tricky part of recursion is coming up with this math. You got to be able to find this solution, this way we break down the problem and shrink that plate of food. So let's go to the next step. Let's try and shrink it down a little bit. So what I've done in this case is I've said, hey, well, let's do it in the opposite order for a second. Let's do the recursive case first. If n is not 0 or 1, then just return n times factorial of n minus 1. Great. In all other cases, return a 1. We don't actually need the else, because if it doesn't go into this if statement, it's just going to return that one. And the else is implicit. Great. So that's much smaller. Can we go smaller? We can. But it's not much prettier, so I warn you. So the next step uses a single line of code and what's called a ternary operator, this question mark here. Basically, it's a way of doing an if statement in a single line, an if-else statement, I should say. So it says, if n is greater than 1, do n times factorial of n minus 1. Else, do 1. But it's really the exact same code as this, just shrunk down into one line. Okay. Now, this is not my animation by any means. You can see it's by peng.com down here, so I'm not taking credit for this. This is an animated GIF that's going to go through this process, and you can see it's the exact same code as the previous slide. If I go back up here, it's the exact same code as this one. The only difference is they're not checking for this 0 case. And because they're running under the assumption that we're always starting from a positive number greater than 1. What if somebody enters in a value of 0 though? Right? Because if we look at this code here, if somebody enters in a value of 0 and it comes in here, it's going to say, well, is n equal to 1? No, it's not. So it's going to go to this else case. It's going to say, return 0 times the factorial of n minus 1. Well, that's great, but that's going to pass in a negative 1 now. Well, that's not going to work out, because that's going to continually keep decreasing and decreasing and decreasing and decreasing, because we're never going to hit this base case of n is equal to 1. So we actually need that n is equal to 0 as well. So it does need to be there. But let's assume that we enter in good data for now and it's a positive number, like, for example, a 5. Now let's break this down. I'm going to bring my eraser over here for a second. Get rid of this stuff so you can see. Now I want you to think of this. We're going to start with an n is equal to 5. Okay? Now, what we need to do is we need to think of what our final solution is going to be. Now, what we're really going to say is we're going to say, okay, well, is 5 equal to 1? No, it's not. So it's going to go to the else case, and it's going to say return the current value of n, which is, well, actually, you know what? Let me do it up here. Return, oh my goodness. Let's see. Return 5, which is the current value of n, multiplied by, well, we're going to call factorial again. We're going to short form this if we can. Factorial I'm just going to write fact of n minus 1. Well, n minus 1 is 4. Well, what is that? So then we go down here, and this is going to return what? We look at this and say, well, is 4 equal to 1? No, it's not. So it goes down here. It says return n. Well, n is 4. 4 times factorial of n minus 1. Well, n is 4, so fact of 3, n minus 1. Well, this needs to return a value too. And you can see that this process is going to continue. And what's going to happen here, as I really shouldn't have written as big as I did, what's going to happen here is we're going to run into the same situation. We're going to get 3 times factorial of 2. And then we're going to have the same thing. We're going to have return. Can't write here. Is my eraser there? I'm going to erase this and just rewrite it because we're getting too messy here, and this is important that we see this whole thing. Okay. So let's try this real quick. So let's say we say this is going to return 5 times our factorial of 4. But that has got to go another level deeper in the recursion. So that's going to return n, which is 4 times factorial of 3. But that, we're still not at our base case yet. We don't know what the value of factorial 3 is, so we got to go down deeper. Return 3 times factorial of 2. We got to go deeper. So we go into 2. 2 is still not equal to 1, so we got to go in again. So we're going to return 2 times factorial of 1. Now this is where things get interesting. Because now when we come in here and n is a value of 1, we see, well, 1 is equal to 1. So we're going to return 1. So now this math occurs. So what happens here is we have 2 times 1, which is of course 2. But now this gets returned up to another step. So that gets returned up. That's a terrible way of drawing it. Eraser here. This one gets returned all the way up here. So now we have 3 times 2. So this piece becomes 3 times 2, which is equal to 6. So now this 6 gets returned up here. So now we have 4 times 6, which is equal to 24. Now this 24 gets returned up there. And now that is 5 times 24, which is equal to 120. And this gets returned to the original problem. So we have our spiral. So we started at 5. We circled all the way in. And then we went down to 4. Circled all the way in. Down to 3. Circled all the way in. 2. Circled all the way in. We got a 1. And that was our base case. And then I'm not going to draw it here because I'll never be able to get it in there. But then it came back out doing 1 times 2. And that gave us 2. And then we did 2 times 3. That gave us 6. Then we came back out again. 6 times 4, which is 24. Came back out again. And that 24 times 5, which gives us 120. So let's look at the GIF animation to see how it works. You can actually see it flow here. That's a little bit more elegant and animated than my written definition here. Oops, let's start it over again. There we go. So we start out at n. We're going to pass in a value of n is 5. So yeah, n is 5. Can't get in there. It comes in here. Now it says 5 times 4. Goes deeper. And it goes to the exact same code again. But this time with a value of 4. Goes deeper. This time with a value of 3. Again, Still too big, goes deeper. And we get down to 2. And you see the equation building up each step just like we did over here. 5 times 4 times 3 times 2, and now we get to 1. But now it gets into this piece. We get a 1. And we have our final result. And that actually gets returned back up the whole chain. That whole chain goes all the way back up. So that's what makes recursion so elegant. As long as you get the math right, the solution just works. Let's look at that. Let's look at that code here for a second. This is the cleanest version of it. As long as you get this math right, everything just works. There's no complication here as we have here. We got to fit through. We have to trace through the code or anything like that. We just basically have an equation. And as long as that equation works, we're good to go. All right, let's keep going here. So how do we actually do this? Well, we do this using a strategy called divide and conquer, which I mentioned before. Basically, that means divide the problem into subproblems of the exact same type. Okay, now solve those subproblems. So each one of those subproblems is going to have its own little solution. Then you're going to combine those solutions to get a final result. Well, that's basically what we did in our previous example over here. We solved the subproblems, and then we combined them through multiplication to work our way back up to get that 120. Man, look how beautiful that handwriting is. Something special. So, quick little example. We see the factorial problem here. We see n factorial is really equal to n times n minus 1 factorial. Well, that's equal to n times n minus 1 times n minus 2 factorial. We've got to see the pattern. And once you've seen the pattern, you realize that this is what really matters. We're saying our current value of n multiplied by the exact same problem, slightly smaller. Once you've got this, you're good to go. That is the trickiest part, though, we're not going to lie. So here we can see each step is the same problem on a smaller data set that will eventually lead to the one truth about factorials, which is 0 factorial is in fact a 1. Basic truth, our base case. So what is in a recursive function? Well, 3 parts really. First is one or more base cases. You may come into some situations, some situations where there are more than one base case. Like in our previous example, we had 0 or 1. Those are 2 valid base cases. Now we kind of combine them into a single base case, but really they're 2. You may also have one or more recursive cases. So this is actually possible. And this recursive case does the hard work of stepping towards the base case. It breaks down the problem to the smaller versions and works towards that base case. Eventually you need to hit the base case or you're going to end up with that infinite recursion. So those are the 3 parts there: base cases, recursive cases, and the step towards the problem. Now, yeah, let's keep going on that one. So we talked about this factorial. We have our base cases, which is n is 0 factorial, and which is the true one. 1 is also 1 as well. And then recursive cases, we can break this down here into 1. N is greater than or equal to 1, or n is greater than 1 in reality. And we get this recursive factorial problem. Now you see that we step towards the base case by passing in a smaller subset of data every step of the process. So the goal of the recursive case is to break down that problem into the problem will eventually be that will eventually reach that base case. If we don't reach that base case, not going to work. So what happens if it does not reach one of those base cases? I already said this like 17 times. You should probably know my PowerPoints a little bit better. But basically we get into this infinite recursion problem and we get our stack overflow error. Let's try and stay away from that. Here's your code, your final code. We see it all broken down and all the different individual pieces. Now, a couple quick tips. This is our final slide of the presentation. Make sure the recursion stops. You got to reach that base case for the 17th, 18th time, I don't know. Limit recursion to one subprogram as much as you can. So you notice our example here. Let's say I have a function A. Let's say a function A, and that guy inside of it calls function B, and that one calls function C, and then that one goes back to A, and then goes B, goes to C. Now, it's not unheard of. In fact, we may even come to some examples in our class where function A may call function B, which then calls function A, as opposed to A calling A. So normally recursion is A calls A, which then calls A. It's a loop, right? It just repeats itself, so we have something more like this. But it's not unheard of to have something like this: A and B. So A calls B, and then B comes back to A. and it just recursively goes around like that. That is perfectly valid. This gets dangerous though. The more you do, the more challenging it gets, so try and avoid it when you can. Anyways, back over here. You will get Stack Overflow errors because it's quite difficult to know how much space or extra space each level of recursion uses. So the more it's going on there, the more memory that's consumed, you're going to run into that problem. Now there is some protection that you can do. You could, for example, keep track of the number or the depth that you're at by some global variable that says, okay, every time you go another layer deeper, you count, keep track of a continual count, and if you hit a certain amount, you just say, no, that's enough, we've gone too deep, let's back out before we crash our program. That's fine. Now that being said, my next point is you should try to, oh, that's not right, where is it? And go to this one first. You should avoid using global variables and recursive subprograms at all costs, with the exception of that safety variable, because you never know which level of recursion is actually playing with the variable. You might be modifying it on the 2nd level of depth and the 17th level of depth, and that may not be good because you're not sure when that's actually happening. So best case, try and keep your recursive subprograms completely self-contained so they're not dependent on anything global. Keep the coupling to a minimum. Back up to this point, only use recursion for problems where it's actually worth it. Remember, all your problems that you can solve with recursion, you can also do with a loop. So make that decision when you first get that problem. Okay, so that's it for this. On the Google Classroom, you're going to find a couple practice problems. Do your best to try and go through those. Ask questions if you have any, some emails, whatever you need to do, and we'll see how things go. I hope this worked out well for you.